go here and get this up on the screen. Beginning. All right. Hopefully everybody on YouTube can, or on at least Zoom can see that. Yeah, somebody here want to verify that? That'd be good. Okay, so this is the monthly meeting of the BSAS. We are happy to welcome tonight Dr. Amber Straughn from the Goddard Space Flight Center, which is a really cool place that I would really like to visit someday. Amber, can I get a tour?
Absolutely. Happy to give you tours if you make it up to Maryland.
A good friend of mine used to work there. I don't know if he's there. He might be retired by now, but he did a lot of black hole stuff at the time. But
oh, cool.
So let's see. So we are doing Unfolding the Universe, which is really a great way to say anything about the James Webb Space Telescope. Amber is an astrophysicist, associate director of Astrophysics Science Division, deputy project scientist for the JWST Science Communications. And that's very good at Goddard Space Flight Center, which is in Maryland, right? So we are going to, let's see, page, go down. And that was back. Oh, that's my regular business. Okay, so we're just going to go straight into your talk. So I'm going to escape out of that and then let you share your screen. Hopefully, have you got the green thing?
I did a minute ago. It's still there. Looks like it's going to work. Should I go ahead and share my screen?
Yeah, go ahead and share your screen.
Okay, sounds good. Yes.
And I might have to throw this back up to
share. Do you see my screen?
Yeah, I do. So let me, can I drag that? Why can't I drag that over? Okay. View options. Hang on. I have to drag it over to the other display.
All good.
And not that way, this way. There we go. We do. Hey, don't be making fun of my icons, man. Okay. So we can go big. There we go. We got you.
Good to go?
Yep.
All right. All right. Well, thanks for hosting me tonight. I'm excited to be here talking to y'all. I don't know if you heard the story of how I got invited to do this. I'll tell it very, very quickly because it's a long story. But I was at a Pearl Jam concert in Fort Worth last September, and I met Tony in the pit after the show. There's a lot more to this story. He can tell you sometime. But anyway, that's the very short version because I'm not here tonight to talk about Pearl Jam, although I could talk about Pearl Jam for a long time too. But I will focus on the universe tonight. So I actually grew up in Arkansas. Oh no, my slides are going a little bonkers there. Okay, there we go. I grew up just not too far from y'all in Arkansas, in rural Arkansas, in fact. And it really was the dark night sky there that got me interested in astronomy from the time I was a kid. I'm a first-gen college student, so I grew up just knowing that I loved the stars and I wanted to figure out how things worked. But I didn't, of course, know any scientists, and my parents didn't go to college, so I was kind of didn't exactly know how to pursue that. But even in my tiny little school in rural Arkansas, I had a lot of great mentors and a lot of great help to sort of help me on the way. And so I went to college at University of Arkansas. Go Hogs. I'll just leave that out there. And I got my undergrad degree there at Arkansas, and then I went on to graduate school out at Arizona State University. I got my PhD in physics at Arizona State in 2008, and then got a postdoc at Goddard, and I've been there ever since, working on this awesome James Webb Space Telescope science team. So that's a very short version of my longer story, but I am, it's a dream job for me, needless to say. I absolutely love it. So I've been working on this telescope essentially my whole career. I've been at Goddard. It'll be 15 years actually, or 16 years this next month. So since the time I was a grad student, have been associated with this telescope. And you know, most of that time was when the telescope was being built. And of course, I'm here tonight to talk a little bit about the science, the incredible things we've already learned the first 2 years. But I don't feel like I can skip straight to the science without talking a little bit about the absolutely incredible engineering of this awesome telescope. So, as I'm sure you all know, have heard the story, this telescope is by far the biggest and most complex telescope that we've ever sent to space. It stands about 4 stories tall. That gold plated mirror is about 22 feet in diameter. And obviously, it had to fold up to fit inside the rocket. And then we unfolded once we were in space. And so this telescope really has been in the works for over 2 decades to get to where we are. Over 10,000 people have worked on the telescope over the course of the past 20 plus years to get it into space. And then, of course, on Christmas Day of 2021, we launched the telescope into space. So I'm just going to play this quick launch video because who doesn't like a launch video? If you can't hear the sound or it's not working, just let me know. I can skip, but it's short. Oh no, it didn't work. Okay, you all probably watched the launch. I would ask for a show of hands, but I can't see you. But I'm assuming a lot of you all actually watched the launch. I was working the launch on Christmas Day, and I was originally planning to work the launch from the Missions Ops Center up here in Baltimore. But as that's the schedule sort of crept more and more into the future, it looked like the launch was going to happen over the Christmas holidays. And so I made the decision to go ahead and go home. I'd had some like family stuff happen over the past year, so I really wanted to be home for the holidays that year. And so I went home and I worked the launch from my mom's couch in rural North Central Arkansas, which was, if I couldn't be at the launch site, second best place to be for launch day. So I will skip the launch video, and this next slide I'm showing here, if it will play. I'm wondering if the screen sharing, I think the screen sharing is doing something weird with my videos. It's not letting me play. Sorry about that. I can link to these so you all can see them, but this is a video showing the telescope actually leaving the rocket payload and making its way out into space. So sorry about that. That video did not show. This video is showing. Great. So as you all know, after we launch, so launch is usually the most stressful part of a science mission, but not for us. So once this telescope launched, we had 2 weeks, a little over 2 weeks of these really intense, complicated deployments. It's not a stretch to say that this was the most complicated deployment that NASA has ever done. And so it started by deploying an antenna so we could communicate with the telescope, as well as the solar array. And then we had we had to fire the rockets to make sure the telescope was on the correct trajectory. And then 10 days after launch, we started actually deploying the sun shield, and this video is not going to play, so I don't know. Oh, there we go. And so this sun shield, I showed the deployment animation all the time when I was giving talks before launch, and every time after I would show this video, someone would just sort of raise their hand and be like, is that really going to work? And because this sun shield had 140 release mechanisms, all these different hinges, we had all these different motors, 400 meters of cabling in this sun shield. The sun shield's about the size of a tennis court, and there's 5 layers. Again, extremely, extremely complex. And so that sun shield deployment was absolutely incredibly nerve-wracking. And then, of course, we had to deploy the actual telescope itself, which you saw that deployment of the secondary mirror coming down. If the mirror didn't deploy, that was a single point failure. That would have been a mission-ending event had that not deployed. But after all of this work, after all of these 2 weeks, we had over 300 single point failures, and all of those deployments worked perfectly. So we definitely had a big moment of celebration after the telescope was deployed, but we still had several months of commissioning the telescope, getting it ready for science. So I'm going to skip over all of that because I don't have time to tell you that whole story. But we had another 5.5 months of essentially aligning the mirrors. So those 18 mirror segments had to be individually shaped and aligned. And then we had to turn on our 4 science instruments one at a time, get them all working up to working order. And then after all of that was done, we took our first image, and this is what we got back. And this, of course, is just a boring star. I mean, I'm sure it's a perfectly fine star, but the point was not to study anything about the star. The point was to make sure that the mirrors were aligned and that the instruments were working properly. And absolutely, there were gasps in the room by every astronomer who saw this beautiful image of this very sharp in focus star. And for scientists like me that study galaxies, of course, what I notice in this very short exposure image is all of the galaxies in the background of this image. So just a super quick test image, and we already had one of the deepest infrared images of the universe. So very exciting. And then, of course, we got on to the primary science of the mission. See if this video will play. It did not, but that's okay. What I was showing in that previous video was a simulation of the early universe, because, of course, before JWST, that was all we had, was simulations of how we thought the early universe worked. And then this was the very first image we released on July 11th, just a little over 2 years ago, of by far the deepest infrared image of the universe we've ever taken. So this, of course, is a galaxy cluster, a lensing cluster. Again, you all are part of an astronomy club, and I'm sure you have been absorbing these images as much as the rest of us. So you all know the story of this image, but essentially here, the thing that struck me the most about this image, as far as just the image goes, is when we took the deep fields from Hubble. So think about the Hubble ultra deep field, right? Days and days and days of exposure. And here we get an image that's even deeper in just a few hours. And so I think right off the bat, with this one of these very first images, we could tell what a powerful telescope that we had. So incredibly exciting. And so now I just want to go through some of the images and spectra that we've released, again, quickly, because I want to leave plenty of time for questions, and talk about some of the incredible things we've learned over the past 2 years. So I know this is a group full of astronomy enthusiasts, so I can show you spectra, which makes me happy because, of course, the images are beautiful, but spectra are where the real science gets done. And so this is a spectrum from that image that I just showed, that first deep field image. And just, I mean, if the images impressed people, this spectroscopic capabilities of this telescope are absolutely incredible. So again, in just a few hours of exposure, we are seeing things, we're seeing these details of these very distant galaxies that we had just never even been able to get close to before. We're seeing all these different measurable abundances of these elements in these incredibly distant galaxies. And so absolutely incredible capabilities. And of course, spectra are a core part of the telescope's function. And again, most what you see in the news are the images because those are what make news for the public. But actually about 70% of the telescope's time is spent doing spectroscopy. So that tells you where the actual power of this telescope is. So I started in the distant universe. Now I want to zoom way back, sort of start from local universe and then step on out. So this was one of the first solar system images that we released. Of course, the colors here, there's a little bit of art to how we use the colors and the different filters to make the images appear this way. And just that choice, which is a little bit of science, a little bit of art. But what you see here, of course, is these incredible image of Jupiter, where the lighter colors, the whites, are showing the high altitude clouds. We found extremely fast jet streams on Jupiter that hadn't been observed before. And of course, here you also see the aurora. Also, within our solar system, of course, we've taken some incredible images of Neptune. We've seen the amazing rings. And then this is the zoomed out version of that same image. And what I love about this is essentially every image we take with this telescope is sort of an accidental deep field. So the point of this image was the planet, but look at all the galaxies that you see. The telescope's just so powerful that every time we take an exposure, we essentially get a deep field, which is great for scientists like me that study the distant universe. And then, of course, we got unprecedented views of Uranus, some of the most detailed studies of the rings that we've done since the earlier missions that actually visited those planets. And then this beautiful image of Saturn. We're getting the ices, again, showing up in the lighter colors here in the infrared. And of course, in addition to planets within our solar system, this telescope has done absolutely incredible science for exoplanets. And obviously, the way we study those exoplanets is by the transit method. So we're looking at the chemical signatures that are arising from looking at the starlight passing through the planet's atmosphere. So from transit spectroscopy, of course, we're able to get very basic information about the planet's star system. But with that transit spectroscopy, when you're actually analyzing the starlight going through the atmosphere, of course, we get these absolutely unprecedentedly clear spectra of these exoplanet atmospheres. So this is just one example of one of the early exposures we took. And again, I study distant galaxies, so I'm not an exoplanet scientist, but all my exoplanet friends tell me that they are completely blown away just by how good this data is and how easy it is to get it. Essentially, you don't have to do nearly as much work to sort of tease out the signal from the spectra here. And it's easy for anyone to see all these different chemical signatures that we're getting here over the longest wavelength range that we've ever been able to access. So absolutely incredible work going on in exoplanet science. And then, of course, kind of moving further out, this is the stunningly beautiful image of the Carina Nebula. When we did the NASA broadcast revealing the first images, we had 5 images that we were revealing that day, and they picked several of us to sort of do the reveal. And I got to reveal this one, which was wonderful because this is, I think, still my favorite image that we've released, just because there's even though this isn't my field of study from just an aesthetic point of view, this is just an absolutely stunningly beautiful image. And of course, there is real science to be done here. The big bright star that you can't see that's kind of on top of the view here, of course, it's a young hot star, and that stellar radiation is blasting down and sort of carving out all these detailed structures that you see in this stellar nursery here. So incredible detail. I think there was over 100 new stars that were discovered in this image alone right off the bat. And of course, we've been able to study other stellar nurseries, as it were. This example here is the Tarantula Nebula in the LMC. And again, you can see here the newborn stars there doing their work of sort of blowing out this cavern with the stellar radiation and stellar winds of those newborn stars. Of course, the famous pillars of creation show up absolutely beautifully in infrared light here. And comparing it to the Hubble data on the left, of course, you can see immediately the utility of infrared light. As we promised, and as you all know, infrared light allows you to see through the dust, to see inside the star-forming regions and find out what's going on there. This is another one of the first images we released last July 2 years ago. So this is the Southern Ring Nebula. So it's the near-infrared view on the left and the mid-infrared view on the right. And we discovered here in this image for the first time that there were actually 2 stars at the center of this planetary nebula. So, and just absolutely stunningly beautiful structure that you see here. And again, I can't help being a extragalactic scientist, but noticing all of the different galaxies that pop through. And then, of course, we've been able to, stepping further out in the universe, study of course, other galaxies. This is from a program called FANGS, and that's an acronym that I can't remember what it means, but it's basically a study that's mapping a lot of the nearby galaxies in both mid and near infrared light. And what you see in the infrared, of course, is different than what you see in the visible. This is another just great example of how having these different wavelength capabilities in space helps us put together a better picture of how everything's working. And I think this is just a beautiful example of what you see in the infrared that you definitely miss in the visible. In particular, being able to see through the dust that we know is ubiquitous in galaxy disks. This is one of the first galaxy merger images that we released. This is the Cartwheel galaxy. This particular galaxy, of course, is the result of the galaxy over on the left crashed through it probably several 100 million years ago and created this spoke-like pattern in the Cartwheel galaxy that you see here. Another sort of sub area of my research is galaxy mergers. So I'm really interested in how this whole process plays out. And these images, of course, are wonderful for the public because they're so beautiful. Just last week, we celebrated our 2-year anniversary of science operations by releasing this image of what is colloquially known as the penguin and the egg. It's one of the ARP galaxies. I don't remember the number. But this also, of course, is the result of a galaxy merger. And in this case, both of these galaxies are comparable mass, but of course you have a spiral galaxy interacting with an elliptical, and so you get all of the beautiful distortions happening in the more gaseous and less compact spiral galaxy here, which turned out in this really interesting penguin shape. And so going even further out, now we jump to the furthest out that we've seen. So this particular result was released just a couple months ago, fairly recently. It's been an absolute deluge of results, very hard to keep up with. Even in my subfield, it's hard to keep up with all the results that are coming out. But this is an example, or not an example, this is the most distant galaxy that we've detected to date. So this is a redshift of about 14, which puts it at about 290 million years after the Big Bang. So the most distant galaxy we've ever seen. There are spectra of this galaxy that confirm that redshift. And this is from the JADES program, which is one of the essentially the deep field imaging programs that has been going on since very early on in the telescope's operations. And again, just like you can just stare at this deep field image forever. At least I can. When these first started coming in, I was pulling them up on my computer and just like scanning through. I mean, they're just so rich. There's so much data here. And of course, one of the really interesting things that we're starting to put together about the early universe is, of course, very puzzling. We built this telescope specifically to be able to look back in time and see this first epoch of galaxies forming. And right off the bat, we found thousands of these distant galaxies and sort of the redshift, 10 and above regime. And what those galaxies are showing us is that we don't really have a good understanding of how galaxies got their start. So of course, before JWST, all we had were simulations of how we thought galaxies formed in the early universe. And what we're finding in the early universe is different than what those simulations showed us. So we are finding, first of all, more galaxies than we expected. They're brighter, and so therefore bigger than we expected. They're forming stars at a much higher rate. And we're finding also these huge black holes very early on in the universe that just none of this fits our model of how we thought galaxies got their start. So it's an interesting and a fun place to be because we set out to find something, we found something, and now we're trying to explain it. So it's very interesting. We don't quite know yet what's going on here with these early galaxies and why they look quite a bit different than what we expected. But it's definitely a very interesting thing. Let's see. This is my last slide, and it's just another example of a deep field image that I wanted to show. This is another program that I'm actually part of called the PEARLS program. And again, it's just an example of an absolutely stunningly beautiful deep field, which again is near and dear to my heart. I've done most of my research on images like this. And of course, what you see here is this just huge variety of galaxies. And it's still just stunning to me that, of course, this is just a tiny piece of sky, right? This is like, less than the width of your pinky finger held at arm's length. And so it really is giving us, this telescope is giving us an unprecedented view of the universe. And it's been an absolute thrill to be on the past couple of years as we're seeing these science results absolutely pouring in. So I'm going to stop here, and I am going to let you all ask any questions you might have. I'm going to stop sharing my screen.
First thing I want to say is my hat's off to the image team, because I mean, yeah, I know I've done just barely enough photography to understand how much work that is and how darn good a job they've done at cleaning up those pictures and making them stunningly pretty.
Absolutely. Yeah, the team up at the Space Telescope Science Institute up in Baltimore, which is the Goddard contractor that operates the telescope and that does all this image processing work, they're absolutely top notch. They do such a good job with this. And yeah, the images are so beautiful.
All right. Yes.
Can you tell us a little bit about what your thesis work is going to be, or your research topic is?
I think he wants to know what the focus of your research is.
Yeah.
Of my research? Yeah, sure. So my thesis was on, so I used mostly data from the Hubble Ultra Deep Field, which was state of the art at the time I was in grad school. But in looking at emission line galaxies, so these galaxies that are actively forming stars, and you can study their properties by looking at their spectra. So the particular work that I was doing as a grad student, and then afterwards, and continuing to this day, is using GRISM spectroscopy, which, at the time I got involved with it as a grad student, I didn't understand how comparatively difficult it is. But of course, all the beautiful spectra that I showed in this presentation was, like a slit spectroscopy, which of course you can do from the ground too. It's the first time we've been able to do what essentially slit spectroscopy from space. But a GRISM is just where you have a grating, that stands for grating prism, and you get spectra of everything in the field, which is great. It's lower resolution, so that's the trade-off. It's lower resolution, but you get a spectrum of every galaxy in the field, and lots of tricky things to deal with there. So you can imagine if you have two galaxies that line up along the dispersion line, then you're going to have overlapping spectra. So there's a lot to kind of sort out. So I spent a lot of my thesis work actually just kind of trying to deal with this difficult data. But I ended up putting out one of the very first science papers on this new instrument from Hubble, doing GRISM spectroscopy. So looking at star forming properties of sort of intermediate redshift galaxies, redshift, around 1. And then another kind of complementary part of my research involves looking at galaxy mergers. Not so much like the nearby ones examples I showed here, like the penguin and the cartwheel, but looking at galaxy mergers through cosmic history. So looking at them in these deep fields and trying to kind of understand how the galaxy merger rate changes over time, by looking at disturbed galaxies or galaxy pairs. And from doing that work, seeing how that relates to how star formation changes over time, to how black hole growth changes over time. So my work kind of focuses on trying to understand those larger properties that govern galaxy evolution, and how those change as a function of time. it's a quick kind of summary of my work.
All right, Tony.
What will be the next iteration after the Webb telescope, or the engineers already working on that?
What are they working on the JWST successor?
Yes, absolutely. So not only are we working on it, but we are almost finished with it. So the next big astrophysics flagship telescope is called the Nancy Grace Roman Space Telescope. The first astrophysics telescope named after a woman, which is cool. So Nancy Grace Roman was one of the pioneers at NASA that got Hubble launched. And so she was one of the scientists, astronomers, and also a leader at NASA in the very early days, that was a sort of behind the scenes advocate for Hubble and ended up getting, funding and support, and in addition to her research. So Nancy Grace Roman Space Telescope is being built now at Goddard. We got it's got 2 instruments. The final one was delivered just a couple of months ago. And so we're in the final stages of putting the pieces of the telescope together. The Roman telescope is smaller in scale than Webb. Of course, Webb was a huge, decades-long mission. And Roman is smaller in size. So Roman's about the size of Hubble, still big, but smaller than Webb. But the key thing, that the science that Roman will do is sort of twofold. So, and it's different from the other telescopes in a few key ways. So whereas Hubble and Webb stare at the universe like teeny pieces of the universe very deeply, Roman sees also an infrared light like Webb, less deep but much wider field of view. So I think the Roman field of view now I can't remember off the top of my head, but it's like maybe 100 Hubbles. So it's a huge field of view for Roman. And the science that we'll be able to do for that, the science drivers behind building this telescope, are to study dark matter and dark energy, particularly dark energy, which of course makes up most of the universe, right? Dark matter and dark energy combined make up, we think, 95% of the whole energy mass content of the universe. So we're building this telescope in this way to be able to take basically 3D maps of all of these galaxies and try to piece together how the galaxy shapes are changing, to help us understand how the very early universe got started, and where we think those sort of echoes happen that caused the universe to is causing the universe to accelerate in its expansion. So that's the first part, is dark energy. This telescope will also enable us to study exoplanets, just because of the way it's built. So we'll be able to detect thousands of new exoplanets in a little bit of a different way than NASA's past telescopes have done. So that's being built now. Launches no later than May of 2027. So it's actually not that far away. We're about to start, like I said, final integration and testing of the telescope at Goddard. And then even beyond that, we're starting now at Goddard, like literally now, setting up the structure or the organization that will help us to start to build technologies that will enable what we're calling the Habitable Worlds Observatory, which is exactly what it sounds like. It will be the first NASA mission that is specifically designed to find life outside the solar system. And so that's going to be the design driver for the Habitable Worlds Observatory. And it's a long way down the road. But we're starting now, and we've gotten funding now to start working on the technologies that will ultimately allow us to build a telescope that will be a true life finder.
Cool. All right, who else? Go ahead.
Other than the known micrometeorite strike on the mirror, have there been any other glitches?
Other than getting whacked by a tiny piece of rock, any other glitches or things going on?
Yeah, so the micrometeorite story. We've had one or two micrometeorite strikes that were bigger than we expected. So we kind of we did expect to get hit by them while we were out there. And the rate that we're getting hits is about what we expected. But a couple of them have been bigger than we expected. So we've actually changed the operating procedure for the telescope to try to mitigate this a little bit. So of course the telescope orbits around the sun. And you can think about, like, if the mirror is facing the direction of travel, then the impacts to the mirror are going to have higher momentum and it's going to be worse. So we essentially operate the telescope where it's sort of pointing backwards from the way it's traveling, so that we lessen the effects of those micrometeorite impacts. So that's the operations change that we've started, and it is helping. Aside from that, most everything has been going really well. We've had one issue with kind of one mode of the mid-infrared instrument. So we've had some issues with one of the filters, the filter wheels. And what we're seeing is the backgrounds of the images are a little bit higher than we expected. We don't completely understand it yet. It's probably not due to just like normal detector degradation, because we definitely didn't expect it to happen that fast. So we're still kind of trying to figure that out. And that's something that, of course, all the scientists that are using MIRI data are working on and understand, and are trying to help us kind of understand the effects of what's going on. But aside from the micrometeoroids, which we've mitigated as best we can, in this one specific mode of this one instrument, things are going remarkably well. And the other thing is, we got such an efficient launch that we have over 20 years of fuel, which is, unexpected. When I gave talks before we launched, the line was always, fuel is our life limiting factor. We expect to run out of fuel before anything else breaks. Now that's probably not true. Actually, we have over 20, I think the latest estimate was like 26 years of fuel. Something will probably go wrong in the telescope before we run out of fuel. So, but that's a good thing. It's a good thing to have fuel for longer than we thought we would.
The ESA was real proud of that.
Oh yeah. I mean, that launch was as perfect as it could have gotten. Yeah.
In regards to the fuel question, is it too crazy to think of any possibilities of later refueling to extend it even further?
So because something else will probably go wrong in the telescope, we probably would not need to do that. That, of course, brings up the parallel question of, could we service the telescope, service the instruments like we've done Hubble over and over? And the answer to that question is pretty emphatically no. The telescope was definitely not built to be serviced. So Hubble is a total exception of the rule in that sense, right? We built Hubble specifically to be serviced, right? It's like the instruments slide in and out, we built it that way. We did not build Webb that way. Even like the telescope fully deployed, those sun shields, I mean, that material the sun shields are made out of, Kapton, is almost, it feels like a mylar balloon. It's very, very thin. And so getting near the telescope, even with any kind of propellants, would not be good. So because the telescope has this very open structure, really, it's just, servicing is probably not going to happen. Now, this is NASA. You never say never. If something went wrong, there might be an attempt to try to go to fix it, either for fuel or, repair. But that's definitely not in the plans. Now, I will say that thinking about the Habitable Worlds Observatory, that telescope is definitely, we are planning to make that a serviceable telescope. Like, that is in the plan already, that we'll be able to service the Habitable Worlds Observatory.
All right, so that'll be in Earth orbit then, not out at the Lagrange point.
No, we haven't decided yet. So it's still so early on. So we don't know. We haven't decided the orbit yet. But I think, people are definitely thinking about serviceability at L2 for sure.
Ooh.
So it's not out of the realm of possibility. Robotic servicing, probably not humans, although maybe, but it's definitely, we're thinking robotic servicing. And there's a big effort at NASA and also even in commercial space about in-space servicing.
Go ahead.
I'm curious.
Yeah.
When might we see a radio telescope on the backside of the moon?
Ooh, radio telescopes on the backside of the moon.
Yeah, so that is not too far-fetched. I mean, there are definitely groups that are thinking about that and about how that might work. I don't know if there are any like NASA funded studies for that, but there might be. It's not completely out of the realm of possibility. It's a really interesting idea. My first undergrad, I did an REU at MIT Haystack. So my first like little small research project as an undergrad was using radio data. So I have a soft spot in my heart for radio astronomy.
Yeah. Yeah.
The Jason galaxy that was 290 million years after the Big Bang, that image looked like it had structure to it.
Yes.
Which implies that if you can see structure at 290 million years, do we expect to see some things earlier than that with a little less structure?
Absolutely. So that's one of the things that has us so confused about these distant galaxies. And the most distant one we found, like you said, you can see structure in it. It's not just a couple of pixels of red light, right? Which is kind of what we got from Hubble. Like there's definitely discernible structure in these very distant galaxies, and not just this one, but others that we're finding as well. And the spectrum of this object shows the presence of oxygen, which first of all is incredible that we can detect that at that distance, but also that tells us that there's already been one generation of stars, right, that have seeded a future generation of stars to be able to see the oxygen in the spectrum. So the fact that we're seeing evolved stellar populations and structure in these galaxies is just like, it's wild. We have no idea. Our theories don't yet explain well how galaxies could have built up the stars and the structure that quickly.
My own heart is in observation, so I'm always up for messing around with the theoreticians.
Yeah, for sure.
To give you some idea of, and I don't want to say an age or a date, but when I was an undergrad, I took a spectroscopy course because to me that's where the information is.
Mm-hmm.
And the university had a wide field Schmidt telescope that they could hang a prism on, so that you could do that thing of getting a spectra for everything in the image.
Yeah.
On glass plates.
Wow, that's impressive.
So it was fun, but it wasn't to the level of, you couldn't at that level really see individual elements so much, except for maybe hydrogen or something. But what you would look at is you go, oh look, there's a white dwarf, and there's you could identify the different spectral types. So it was
Yeah.
a lot of fun.
Very cool. That's great.
Go ahead.
Supposing that we can see, if we stare at it long enough, and we can go back beyond the 200 million that we're looking at now, what could that look like? Does anybody have a theory as to what that might look like?
So is there a limit? How far back can we see with JWST, or do we know?
I don't think we really know yet. The JADE survey, the one where we found the most distant galaxy, so far is the deepest image that we have. But of course, we're going to keep taking data and stacking it, and that's going to allow us to go deeper and deeper. So I don't know. I mean, it all, I guess, depends on the red cutoff, the wavelength cutoff, which is 28.5 microns. And so, yeah. But again, it's not like straightforward math, right? Because it all depends on how bright those galaxies are. And so if we keep stacking data and keep getting deeper and deeper, yeah, I think we'll definitely find galaxies that are more distant than that'll break the record that we've just set again. And we know that they're there, right? That's the interesting thing. They have to be, because the ones that we're finding now are not the primordial galaxies that we sort of set out to find. So I don't think we know.
I don't know at what redshift you redshift out of the range of the instrument.
Yeah, I feel like I did that math a long time ago, and I don't remember what it is. But you know, I mean, from a sort of functional standpoint, you know, it has a lot to do with brightness. Which again, these galaxies are brighter than we. I mean, they're so much brighter than we expected. So if you had a really bright booming galaxy that, you know, would be above your detection threshold, yeah, there is ultimately a redshift limit, and that's pretty simple math. I just haven't done it in a while, so I don't remember what it is.
Oh, that's pretty cool. Yeah.
Just how good is this spectroscopy? Those spectrum look really detailed. Just how good are they?
So how do you measure good in spectra? How narrow maybe? What's your, you know, line resolution?
Yeah, so there's a few different ways to do it, but yeah, I mean, it all kind of comes down to signal to noise, you know. So how much of a signal you can actually get out of the noisy spectra for these very distant galaxies. I didn't show the spectrum of that redshift 14 galaxy. I don't think it's even in my backup slides. I should put that on there. But it's not pretty, you know. I mean, it's messy. It's very, you know, it's not as clean as the exoplanet spectrum that I showed, for example, or even the spectrum of the early galaxies I showed earlier in the talk. So, but again, the fact that we're getting, it's above signal noise of 3, right? And so that's, you know, that's kind of, for astronomers, that's pretty good. 3 to 5, you know, if you get a signal noise of 5, that's good. And of course, that's just measured based on the strength of the line as compared to sort of the baseline of the spectrum. I've only got a couple more minutes, so maybe another question, and then I'm going to have to log off.
Go ahead.
So is anybody seriously considering that the Big Bang actually happened much longer ago than we thought? Or is anyone seriously considering that the Big Bang just didn't happen?
Yeah, I think I heard that. So the short answer is, first of all, no, we're not really considering any other theories. The Big Bang definitely still seems to be the best, you know, theory of the universe from lots of different observational angles. And even though these results from the early universe are a little bit perplexing, or a lot perplexing, they're not breaking any fundamental physics, right? They're really not causing us to rethink our theories of the universe or of how the universe got started in the Big Bang. So it's not that ground shattering of a situation. So some of the theory work that's going on now, and I'm an observer. I'm not a theorist, but I have theorist friends, and they're all, you know, working hard to try to figure this out. But some of the sort of theories that are being looked at now, or some of the ideas of why these galaxies are different than we expected, I feel like it's probably something to do with the efficiency of star formation in the early universe. Since the components of the galaxies were obviously drastically different in terms of just elemental, you know, makeup, I think there's probably something going on with the physics of star formation and how efficient that process is. I think there's always, you always have to take into account also the sort of the external effects on the galaxy as well as the internal effects on the galaxy, right? Feedback. So how these first generations of stars are affecting their surroundings, as well as, you know, the pristine gas from the early universe that is feeding in on the galaxies, right? It's a very chaotic environment. So I think we have to refine some of the details of the physics of star formation, most likely in the early universe. But that's doable. We're not breaking any fundamental theories of physics here. So that was a long-winded answer to say we still think the Big Bang is the best theory of the universe.
Science camp happened here last week, and I was going to try to turn this. The stage is full of model Hubbles.
Oh, I love it. That's wonderful. That's so great.
That's pretty fun.
Great.
Anyway, that it? One more?
This is more a philosophical question.
Big Bang was it? Okay.
We humans are an arrogant and pesky bunch. What do you think would happen to society as a whole should we discover an exoplanet where their own version of a web staring back at us?
Isn't that wonderful to think about? So I think the heart of the question there was, what do we think like the reaction will be? Is that yeah. So yeah, wow. Who knows? I mean, definite like fundamental human paradigm shift, right? To discover life, and an advanced conscious life that would be able to build a telescope. It's very, very interesting to think about. I worry about us humans sometimes. And how we would deal with a discovery of that magnitude, given that we don't always have the best track record of dealing with big monumental things. But no, I mean, what an incredible discovery that would be, because we all ask that question, right? Are we alone? That's one of the driving questions of NASA science is, are we alone? And that's why we're building telescopes, to try to understand that, to try to see if life is out there and how common it is. So yeah, to be determined.
TBD. All right, I really want to thank you for your time. I think everybody found this extremely interesting, and yeah.
Thank you.
We'll look forward to more science from Webb.
For sure. Thank you so much, and thanks again to Tony for inviting me.
All right.
Bye-bye.
Bye-bye.
Bye.
Okay. Oh, we had an ask to unmute. Well, don't have to ask the question. I'm not good at this. So now comes the boring part, right? And yeah, the spectra are so much fun. Again, when I was an undergrad, there was a symposium, and a bunch of people came that were not physicists or astronomers, and they put a spectra up, and yet they're nowhere near what they are now, right? And so there was one line, and the guy goes, well, this is hydrogen, whatever, Lyman alpha, and it has a redshift of this. And the people who were not astronomers in the room, their heads are exploding. They go, how can you say that one line is that? And they go, because when you redshift it over, like that's all you got. Literally, they can watch as the redshift progresses with different things. And that was the last one standing. So they knew what it was, but it's just, yeah. So we're going to have to go to, let's see, this gets to be more fun. I want to put the PowerPoint back up here. So shrinky dink. No jokes about my stuff. Not that way. If I could have made it do it the other way, I cheerfully would have. I should do this every month until I get good at it, actually. Beginning. Okay. Oh, except that I have to wait. I have to share screen or something bad will happen, right? That is looking through seawater at Pebbles. Actually, it might be Lake Michigan. Sleeping Bear Dunes National Park. Okay, so it's going to be this screen and share so that the nice people at home can see it. And then we can run this from beginning. Right, go. There we go. All right, so that's what we had. Then we get to do the monthly meeting part. Yay. Hopefully everybody that's here, that's a regular member, we put the minutes in the newsletter. So hopefully you got a chance to read them. If anybody ever finds anything egregious that needs correction, please let us know. Otherwise, they'll stand as published. Is Keith on? I don't think Keith was going to be able to make it tonight. I know we have something really close to 200 members. So yeah. Let's see what we had. We have we had 159, 160 roughly a year ago, and now we're up to 195. So that's kind of fun. You know, we'll have to put out more chairs. That's all I can say. Oh, I should say we do have a little bit of money. I actually did print that out. We have a bank balance of $8,089, and that's why I print this out, and 38 cents. We just paid our astronomical league dues, and since we have 195 members, it ends up being a chunk of money. It's we pay $6 a member per year, and that gets you the Reflector magazine, and it also gets you cute little pins if y'all will work on some of the observing programs. So you should definitely do that so we can get some of that stuff. We have $426.59 in PayPal, and let's see what else we got. So we do have loaner equipment. If anybody's interested in trying out a particular type of telescope before maybe you run out and buy your own, this is a good idea. We have a couple of nice Dobbs. We have a couple of what I will call the typical telescope you might find in a department store. So those are good because they'll teach you what you do not want to buy. Okay. And it's not that they're not usable, they're just painful. That's all. But if you can stand it, you will appreciate everything else you ever use. We do have a nice website, and you can tell that the last time I updated it was on Saturday night when we thought we weren't going to be able to see anything. But Chuck was there anyway. And Chuck, what happened?
I did solar observing early, about 15 people there. I did a moon day exhibit with Apollo to Artemis kind of spacecraft models, and probably had about 10 people for that. And then I was packing up as it was getting dark, because obviously it had been cloudy. After I did solar until about 6 o'clock, then the clouds came in. Okay, that's going to be done. Started taking down my stuff. Sun was taking down part of the scope. And then I happened to look up and saw a couple of the summer triangle stars. And then started looking a little closer, and hey, there's quite a few stars up there. So just my son and I were there. We reset up the scope, didn't finish taking it down.
Where was it?
Montgomery Bell.
Montgomery Bell on Saturday night. Okay. July 20th. And then a few people walked up. This is just outside the Montgomery Bell campground. So we had several people there that were there for the star party, that had heard about it or saw it on Facebook, whatever. And then more people came, and then more people came. We ended up with about 25 people. Had good targets of stars. I did see the Ring Nebula, so it was clear enough to see it, and really good views of the moon. It's full moon, to be able to show them different things on it. Isn't that pretty nice?
So you cannot spot forecast around Nashville. It's just really hard.
White. It said it was white.
Yeah. So you can see at the bottom of our webpage is the Nashville clear sky chart, and you know, that's not real hopeful for the next several days. We kind of got stuck in a rut here, but anyway, and I actually added a what is a star party thing, because that is the most frequently asked question. At one time we had a group that called us up and wanted to know if they could have food trucks come. We're like, it's not that kind of a party, okay? So, but we do have some coming up. Of course, we'll be back here again, and since we're done with tonight, I should go home and re-up for the next set of dates. But
Is that out of focus, or is my vision having
it's not the world's best focus, and that could just be the resolution that I copied it from the screen, and it's on a bigger screen now, because the poster looks actually not too bad. So you can get, before we get to 100 years, you should get the 90th poster. We'll have to do another one at 100. All right. We do have a Facebook page. Some few people do follow us there. We also have Twitter and Instagram, and everything is BSAS Nashville, so that it's easy to remember. There is next Thursday astronomy on tap downtown if you want to drink beer and hear some cool astronomy. So that's always fun. Is it really?
Yeah.
No, oh, sorry, that's Wednesday. Wednesday, August 31st. So, and there's our I'll look at that. So this is our Twitter page. I'm not used to seeing it that big. Instagram. And then for members, we have a group, Google group. It's really fun to ask questions, see what's going on. I think the best use of it is where it says Natchez Trace tonight, so that you can say, hey, for the monthly private parties that we have a permit for at 2 different locations on the Natchez Trace, are you going? Because it's a really lonely place if you're the only person out there. So it's a lot more fun if a couple people are going out.
And it's not necessarily fun, safely.
Yeah. So this is what I'm doing every time it's clear enough to go out and image Corona Borealis, where the 2 green lines are. I promise you there is a tiny little 10th magnitude star that hopefully in the next few months will not be a 10th magnitude star anymore. So we are watching that. It's supposed to go and have a nova outburst here over the next little while.
Is that where the green lines are?
Yep.
Okay.
And there is actually a dot there. It's
And the projection is that it should be as bright as Gemma.
yeah. So it should get to naked eye visibility for a very short time, but it would be very cool. So I really would like to catch it on the way up. I mean, but I'm sure that Twitter and everything else will know about it when it happens. So
What's the latest predicted?
they think before the end of September.
Okay.
So we're kind of running into that here. So and you know, the star will go when it goes. That's some poor white dwarf is having stuff dumped on it, and at some point it won't take it anymore, and we'll have a big explosion. I'm not going to say anything to the love of your life, the lovely Victoria Holland. Yeah. So yeah, and there's our Night Sky Network page. We do keep a calendar there that if you remember, you can see the private star parties here. And it's just a ton of cool stuff on that site. Featured is Observe the Moon Night coming up in September. So it is really nice and useful. They also have a lot of cool little activities. If somebody asks you to show up somewhere and do some little activity, there are lots of really cool. And they not only have the activity and what you might need to do it, most of them are really simple things. They have a video of somebody doing the activity so you can see how it should go. So it's very nice. Yep, there's Finding Hercules. And there's where T Corona Borealis is. So yeah, normally in the night sky, what I can see is find Arcturus, right? You can do this, and then you can make the triangle go down to here. And if I see anything else, I'm going to wonder if it's gone, because yeah, from my backyard in Nashville now, you know, we went out to the Natchez Trace State Park a couple weeks ago for the last new moon, and you could actually see the whole crown, which is nice. And they have nice monthly star maps that kind of highlight, hey, what's cool in the sky this month? And especially for folks that are trying to become familiar with the sky, you know, little things like arcing to Arcturus from the Big Dipper, the summer triangle, where is that? So how you can start to find your way around. So yeah, there was, I don't remember how July 6th went. I know it was hotter than Hades. So did anybody go out to the trace that was here? I just remember doing it was actually not too bad out on the other side of the river. It was just hot. And then we did have a star party at Cornelia Fort. It was a nice night. Roy brought his dog. That's how you know it's a nice night, because he won't bring it out unless it's nice. And then you heard about Montgomery Bell. Oh, you didn't update that one very well. I got this from Tom, so looks like we'll be going out to private star party on the 3rd. And then he always likes to mention that please download the permit and have it on your phone or something, because every now and then the rangers come around and get persnickety about that. Yeah, it's a national park, but you can't hang out at night. So, and then we'll be back at Warner Park on the 10th. Maybe we'll see a few Perseids. Maybe.
How do you download the permit?
It's on the group site. So somewhere there is, and I think he has it tagged, but if you can't find it, if you search for it under the group emails or under that group listing of messages, it's a download from there. But if you have any trouble, just email info@ and somebody will send it to you. So there's the sort of the cool groupings or fun things that are going on. I'm pretty sure either while we were there or shortly thereafter, that the moon ran over Spica at the star party. Yeah. Well, it was cool because it was the dark side that was running over it. So that was cool. And a couple of nice planet groupings that are starting to get in the morning sky, where maybe it's not a totally impossible thing to see them. And so that is August the 5th at 2:30 in the morning. Maybe the dog needs a walk, okay? So the Pleiades are starting to come up. Mars and Jupiter are kind of pretty. They'll move into the evening sky later in the year, so we'll wait for it. And next month, you get to hear me. And if I'm lucky, I'll have a voice. I'm doing a talk for the Garden Club in Fairfield Glade in the morning, and that's going to be about light pollution, which is near and dear to my heart. And that's a whole separate, we've rechartered Dark Sky Tennessee. So we have a Tennessee chapter of the IDA, and my goal is to have a meeting by the end of the year for Middle Tennessee. So we're working on it, but it's just slow steps because none of us have any time. But get people to turn the lights down. I need that, which reminds me, I need to poke Metro because, yay, we're putting up LED lights, but boo, we don't have any clue what kind of LED lights really. The only saving grace is I have heard they're putting up ones that are dimmable, which is really nice. Not Phoenix, but oh, shoot. Anyway, cities have found that it's amazing. You can turn the lights to like 50% or less after midnight. No one will notice. You don't ask, you just do. Because actually people are not out, most of them, at that time of night. So anyway, that's pretty much where we're at. Does anybody have any questions, comments, cool things we should talk about before we leave? Whoa. If anybody has a payment, I can take that after the meeting here. I really can't think of too much else. Let's see. I was going to see if I don't see Tom on here either. So, all right. Well, thank you all for coming. I think that was a really fun talk. And yeah, thank you, Tony, for that invitation. That was very good. So, thanks for coming.
We'll work on another one.
There we go.
Yeah.
So then I'm going to. Aren't those cute?
That looks like it could be a mailbox.
Then we're going, right? We're going to stop sharing the screen. And so thank you guys for hanging out with us online. We will see all of you next